What time is it? It's science time.
Science time. Let's all stop and just unwind. 1, 2, 3, 4, here we go. Learn so much your brain explodes. Lessons so cool, so fresh. Beat so big you'll lose your breath. Learning facts and real cool stuff. Scream for more, can't get enough. It's science time. It's fun, you best believe. Explore and learn new things. Come and join me, please.
I'm Mr. C, and this super smart group is my science crew. Lila is our notebook navigator, Alfred is our experiment expert, Riley is our dynamite demonstrator, and London is our research wrangler. Working with my team is the best and makes learning so much fun. Actually, you should join us. Today, we're talking about rockets and propulsion. What time is it? It's science time. Hi, everybody. Wait a minute. What is this? USSRC, Huntsville, Alabama. Is this really happening? Space camp? Space camp? We're going to space camp? Are you guys ready? Grab your crew. We're going on a field trip.
It's science time. It's science time. It's science time. It's science time. It's science time.
Welcome back to DIY Science Time. My name's Mr. C, and I'm so excited that you're here to be part of our science crew today. We are at the U.S. Space and Rocket Center in Huntsville, Alabama, home to Space Camp. That's right, we're talking all things propulsion and all things space. It's going to be out of this world. Are you ready? Let's go.
It's science time. 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 It's so much fun. Learning fun for everyone. Everyone. It's science time. Yes, you best believe. Explore and learn new things. Here with Mr. C. It's science time. Every day. We know it's awesome. We know it's great.
Hi everyone, and welcome to Space Camp. My name is Lane, and I will be your crew trainer today.
Lane, it's super nice to meet you. I'm so excited to be here. So I know this is Space Camp, but what is this space specifically all about?
So this is called the Mission Center Complex. This is where we run all the simulated missions on the Moon, Mars, and lower orbit.
So you said simulations. Does that mean I get to do a simulation with you today?
You do,
All right, so what's the first thing we need to do?
we get suited up.
All right, let's go. Pants, boots, helmet, coat. Right from the start, our mission required a tremendous amount of teamwork. Lane and I had to work together just to get suited up, and a little bit of training so that we could successfully complete our mission to repair the ammonia tank. We were hoisted up alongside the space station with a mission to repair and replace a faulty ammonia tank. This is a critical repair that mission specialists actually had to perform in space in 2009. We were only working for about 45 minutes compared to the 6.5 hours that the astronauts spent floating outside in space. They were unhooking valves, moving equipment, and reconnecting everything. This is just one of the many, many missions that Space Camp attendees get to experience. What an amazing adventure to get to work together with Lane to ensure that the International Space Station and its crew were all safe and comfortable. So that was amazing. Thank you so much for taking me up into space and doing that simulation. That was such hard work, but having a teammate and a crew member like you was amazing. Thank you.
Exactly. It requires two to make it work.
Teamwork.
Teamwork.
Yes.
Great job.
Yes.
I've been reading a book about anti-gravity. It's impossible to put down. We're going to try some out-of-this-world activities today. You'll need the following materials to follow along: paper, aluminum foil, tape, scissors, straws, plastic bags, cups, glue, and of course, you know what matters most, your super stellar science notebook.
A science notebook is a tool that every scientist should have, and it gives us a place to record all of our learning. Taking good notes and being organized allows us to be better scientists. A science notebook allows us to go back and review all the data and information we've gathered during our experiments. Plus, it allows us to share results with other scientists who might be interested in learning more about what we've discovered. Whenever you see the notebook pop up on the screen, like this, it's a reminder that this is a good place for us to jot down new information. You can see I've already added a title and a list of materials for today's activity. Our crew is still going to have lots of information to collect and organize as we go through the experiment, so keep your notebook handy. Most importantly, the more you use the science notebook, the better you'll get at taking notes and recording data. If you don't have a science notebook yet, download a copy of Mr. C's science notebook from the website.
Working on the space station sure makes someone hungry. And let me tell you what, if I'm in space, I'm going to need food. But I realize that in space, they don't have gravity. So when you open up a container, things will start to float around. So transporting food is probably really important, getting it to space and keeping it in space without it getting all over the place. So what we're gonna do is we are going to engineer our own containers that will allow us to transport food here on Earth, but more specifically, thinking about what we could use in space and whether or not it would be successful. All right, let's give it a try. So the first thing I'm thinking is like a squeeze pouch of some sort, kind of closed off, and we'll tape the edges. And then here at the top, we'll have like a little piece of like tape or a seal that will lift, and then we'll insert the straw so that we can eat our food. Eat our food through a straw. So we're essentially exploring the engineering design process. We have a task, get food out into outer space. So we need containers for that. Could be a plastic pouch, maybe a foil tube, or even like a plastic cup of some sort. But the challenge is whether or not it's going to work. And I'll be honest with you, having what I have here may or may not work, but that's the cool thing about the engineering design process. If it doesn't work the first time, you come back and you try it again.
Packaging food like this means it is able to keep all of its nutrition and taste for almost 5 years. All of the food on the International Space Station has all of the water removed. Removing the water reduces weight, and it makes food safe to eat for a long time.
All right, so check it out. I made a couple of different containers, and I'm really excited to share them with you. The first two containers are very similar. These are maybe some sort of containers for drinks. So they come sealed, they're airtight, and maybe there'll be something in there like a powder where the astronauts can add liquid to it in outer space, and then when they're ready to drink it, they can pop it in, add the liquid, and then you can have your drink. Ah, delicious. Air. Brought to you by the atmosphere. And then you have this contraption. Now, this could be used in two different ways. This looks like a toothpaste tube, kind of, but what you can do is there's a hole in it and it comes sealed. You can use a straw if you want, and you can pop a straw into it and you can drink from it. And when it's all gone, it like vacuums itself out, right? Or you could drink from it like this. Yummy. So you could actually try it just like that and put food in there, and then it would hold and be self-contained in that container. This is my favorite. Could be a food or a drink, but look at this. I designed this to be a pouch, and it has a straw. and it's all sealed off. And then when you're ready to eat, pop off the straw, you lift it. Oh, I gotta work on this. Ah! I've gotta redesign this. And then the straw goes into the pouch, maybe. Whew. I'd be hungry as an astronaut. But then the straw goes in and it's all self-contained. So then you have your meal. Yummer. That is delicious blue space food, right? Now, I know realistically astronauts aren't taking this into space, but these are prototypes and these give me shapes of things that I might want to actually build. And then I work with engineers to find the right materials to make this from so that it seals properly and the food is safe and is able to be stored for a long time while the astronauts are working at the ISS.
It's science time. It's science time.
Well, hello and welcome to the U.S. Space and Rocket Center.
Thank you. It's excited to be here.
Great. So, are you ready to talk about propulsion and rocketry?
Yes, I've flown a long way to get down here, so I'm super excited to see what kind of engines can get me back home.
So, airplane engines are quite different from rocket engines. So, are you ready to launch into outer space?
I'm definitely ready to launch in outer space. And speaking of which, this space here is amazing, wouldn't you say?
Yes. So, we here in the Saturn V Hall at the U.S. Space and Rocket Center celebrate the Apollo program with NASA's most powerful rocket of historical means that took us to the moon the first time. So we have above our heads the 363-foot tall rocket, the first one ever made. So let's talk about some propulsion.
I'm ready. Where do we start?
At the beginning.
At the beginning. Let's head back.
We're situated here, ready for liftoff. Checklist A71 Beta Niner. Roger, launch vehicle.
We're currently under the first stage of the Saturn V rocket.
The first stage. So I have to ask, what is a stage?
So a stage is a part of a rocket that is the fuel container. It is the gas tank. So it holds the liquid fuel, and once it is spent, it is jettisoned. So then the next stage can ignite.
So when you say the next stage, that brings me to the question. So this first stage, it looks like it has 5 rockets? Five engines?
Yes, it has 5 F1 engines. So all 5 of those engines, when they ignited, it produced 7.5 million pounds of thrust to lift this 6 million pound rocket from Earth to its destination, the moon.
All right, so the key word is stage, and we're propelling this massive thing into space. So after the first stage goes through its phase, so to speak, there are additional stages? Is that what I'm understanding?
So
and do they all have engines?
There is the second stage, which has the 5 same arrangement as the F1s above our head,
Okay.
but the next engine is called a J2. So those J2s produce a 100,000 pound of thrust individually. And then you have a single J2 on the third stage with that 100,000 pounds of force type.
So if I know we're underneath these right now, these massive engines, but is there a place where we could actually look a little closer to see what one of these look like?
Yes, so they're mounted in their arrangement now on this rocket, but let's get a closer look at one that's at ground and eye level.
All right, let's check it out.
So we are now at eye level to the F1 engine, where we saw earlier above our heads all 5 in its configuration on the aft end of the Saturn V rocket.
All right, so this F1 engine is propelling this massive rocket into space. And the question is, everyone's wondering, what kind of fuel does something like this use to be able to do that?
So this engine uses a mixture of liquid fuels, kerosene and oxygen as its oxidizer. So it is burning this liquid fuel, and all 5 of those F1 engines produce 7.5 million pounds of thrust to launch this 6 million pound rocket into space.
Now, I don't have liquid fuel like this at home, but my brain has been working since we've been talking today, Joseph, and I'm thinking I might be able to actually build one of these rockets. Do you think that's possible?
I think that's possible, to build a smaller version of this rocket in your home.
So I think I'm going to try to do that. And you have helped so much today. All of these things create massive amounts of pressure. and thrust,
So
which
all
makes
of
this
these
happen.
fuels are pressurized inside of this rocket, inside that fuel tank, and it's pressurized so that it provides that major amount of thrust for that burning potential. And speaking of all this, I challenge you to build your own rocket at home. Using what you've learned here, seeing what you've seen here, take this information back and build your own version at home.
Challenge accepted. We're gonna build a DIY rocket at home here in just a moment. But before that, I wanted to say a big special thanks to you, Joseph, for taking your time, spending with us here, and propelling our knowledge about rockets to the next level in outer space. Thank you so much, sir.
Thank you.
Challenge accepted. We're gonna use a balloon for my rocket. This balloon uses air to power it. When I let it go, in theory, the air is gonna rush out this way, the balloon should go that way. But if I let it go without any sort of control, it's just gonna fly all over the yard. So what I've done is I've attached a straw to a string from one side of my yard to the other. I'm gonna put that on there. And blow it up a little bit more. Here we go, bring this back. Now this is a single stage rocket. Single stage meaning it only has one fuel source and it only has one engine. So we're gonna see how far it goes. All right, here we go. In 3, 2, 1. Oh, it only went halfway. So what we're gonna try now is we're gonna try building a 2-stage rocket using some squealer balloons instead of a big balloon, and we'll see if it actually works. All right, so here's my 2-stage rocket. Let me show you how this works, in theory. This one is going to let all the air release. And once all the air releases, the collar here is putting pressure on this balloon to prevent the air from coming out. Once the air releases, it's going to allow this air to start releasing, and hopefully it'll continue traveling down our string. I don't know if it's gonna work. There's only one way to find out. Let's get this hooked up. So I want a little bit of slack. Oh, I think I've got it too tight here. I'm gonna see what happens. I'm gonna unhook this one and unhook this one. Oh, it didn't go anywhere. Actually, it did. So we had an initial problem with launch. Let's give that a try again. I think it's too tight. I think I need some slack so that I can get everything kind of balanced so that it'll be able to flow more freely. And I'm trying to get them all lined up so that they're sort of straight. Oh, the wind is so bad. All right, we're gonna give it a try. It looks like it's gonna work. We're gonna let the wind die down. We're gonna wait for a break. I'm gonna get these ready. Okay, stage 2 is unleashed. Are you ready? In 3, 2, 1. All right, let's give this another try. Ah! Yes! It was successful. It didn't work great, but the first stage, it was like bound up. It didn't want to actually like move very easily. So it's like the rocket was stuck, maybe I don't know what's going on. But once the first one released and the neck of the second stage was able to release the air, it took off and went all the way down. That was so cool. I think you should give this a try. You can do a single stage rocket, just trying with one balloon, or you can try like I did and make a double stage or a 2-stage rocket to see if you can get your rocket to go even farther. Give it a try. Science is so much fun. US Space and Rocket Center! Challenge successfully completed.
Hello, I'm Bob Newsflash for WAIR.
the pressure continues to build as we wait our resident science expert Adam Splitter's next demonstration. He's been planning this experiment for quite some time, and you can certainly feel the excitement in the air. Let's connect with him now. Adam, we're so excited to see this is finally happening today. What can you tell us?
Thanks, Bob. Adam Splitter here with WAIR, and today we're talking about Newton's third law. That's right, I'm so excited about this one. I've been waiting and reacting to the weather and making sure we have a perfect day. In fact, the wind is blowing, and it's a perfect day to get the rockets out and to shoot some amazing, amazing liquid nitrogen rockets up into the sky. Now, kids and parents, I want you to remember something. This is not something that you should try at home. Repeat, do not try this at home. Home, home. All right, so let's talk liquid nitrogen. It's minus 320 degrees Fahrenheit, and when it gets out into the air like it is now, it starts to boil, and that means it's expanding, and it expands about 800 times its size from a liquid to a gas. And what's really cool is liquid nitrogen, we're gonna use a bottle of water and liquid nitrogen to do the experiment. Now, liquid nitrogen is clear just like water. So here I have water, and I have this other liquid here to show you that liquid nitrogen sits on top of water. That's because it's less dense. And because it's less dense, when I turn this over like this, the liquid nitrogen races to the top. And because it's expanding 800 times, it's going to cause pressure. It's going to shoot the water out, and hopefully we have rockets that'll soar high into the sky. Are we ready, everybody? Are we ready? Okay, what we're going to do really quick, we're just going to try this. We just got to try it. All right, I've got some goggles I need to put on. Safety is really critical and important. Like I said before, kids, you should not be trying this at home. Parents, you should not try this at home either. In 3, 2, 1. Where'd it go? Oh my gosh. That was so awesome. That was so cool, blew off my mustache. In 3, 2, 1. Oh my gosh, that is so cool. Every time. My mind just went, poosh. That was amazing. I can't believe that is the experiment that we were able to do today. Equal and opposite reactions, Newton's third law, rockets here at the park, something none of you should try at home, but you're here to watch it with me, Adam Splitter. All right, back to you, Bob. Oh my gosh, that was so amazing. Can you believe it? Oh, that was so cool. We're live? Oh, sorry, Bob. Back to you.
Fantastic, Adam. And there you have it. Thank you for tuning in today for this crushing news here at WAIR, where our reporting is always a breath of fresh air.
This is the Apollo 12 moon rock. This rock is an igneous rock, which means it was formed from a volcanic lava flow. As the lava was flowing, it began to cool and solidify on the surface of the moon. And just like the surface of the moon, the rock is gray in color. Be your own geologist and study rocks here on the Earth.
Mission Control, this is DIY Science Time crew member Lila checking in to confirm we've had an amazing day today learning about space. Our activities today have been out of this world, and I've been working to jot down all sorts of amazing notes for the team. I've included information about the International Space Station, Saturn V, astronaut food, and propulsion. Plus, that rocket experiment Mr. Seated was so cool. I wonder what might happen if you changed the size of the engine. Or you could change the mass of the actual rocket while keeping the engine the same to see how that might impact its flight. I think that's something you and your science crew should try at home.
Wow, what a busy day. I just flew back from Huntsville, and let me tell you what, my arms are tired. No, but on a serious note, isn't it amazing all the work and all of the engineering that takes place in outer space? Astronauts have such cool jobs, but they really do a lot of work to prepare for that travel into space. And it all starts with taking notes, like in your science notebook. If you don't have one of these yet, make sure you download one from the internet. You can get this and keep track of all of your experiments that you do each and every day. Speaking of experiments, my food container? Sort of iffy. But while I was down there, I got some official astronaut ice cream from space camp. I'm gonna open it now and see what it tastes like. It's an ice cream sandwich. Oh, and it's freeze. It's completely freeze-dried. I wonder what this is gonna taste like. Before I get into this, I wanna say, keep exploring, keep having fun, keep learning, and remember, science is wherever you are. The strawberry is really good. Yummy! Let's get to my favorite vanilla. Oh my gosh, that's amazing.
It's science time. 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 It's so much fun.
Let's just keep rolling. I'm gonna finish my sandwich.